All right, so we're on our third problem for our hypothesis testing about a population mean. Problem states the average decibel level at restaurants during the busiest hours in the United States is about 80 decibels. In an effort to cut down on noise level, a noise-reducing foam was developed to be applied to the walls and ceilings of restaurants. A study was conducted at several restaurants throughout the city, and the decibel levels are shown below. Test the claim that the foam makes a difference in decibel levels. And for this type of problem, we are given data, and we are only given data, meaning that we don't have a mean, we don't have a standard deviation, we pretty much don't have anything except for the data. So we're going to have to determine a whole bunch of things for this problem that we didn't have to determine for previous problems, but we'll still do it as quickly as possible. So here's the data that's given, and we still will have to deconstruct this, but let's just take a look at part A. It says determine whether this is a test of mean or proportion. We already know it's a test of mean. And determine if sigma is known. And in this case, sigma is definitely not known because we're not even given any kind of a standard deviation. Also, we can do part C real easily. Determine if this test is a left tail, two tail, or right tail test. Well, this is a two tail test because if we look at the final statement, it says test the claim that the foam makes a difference. Well, that expression makes a difference. It would mean make a difference either way. This foam, hypothetically, could actually increase noise levels for all we know. We hope it decreases noise levels, but we just want to know, does it make any kind of a difference at all? We still need to find the things we found with the previous tests. An X bar, which we don't have. N, well, that's an easy one to figure out. We just count up the number of values that we have. Remember, N always stands for a number of things. Nu, which is pretty easy. We just would take N minus 1. Mu, that's the value that we're testing against. And because the average was 80 decibels at the busiest hours, that's the value we're testing against, so that would be our mu value. Our level of confidence, well, neither a level of confidence nor a level of significance is given. We go to the default value, which is 95%. That would mean that my alpha is 5% or 0.05. And sigma, of course, the population standard deviation is not given because all we're given is data. We have S, and that we'll have to do on a spreadsheet, and we'll also do X bar on a spreadsheet. This is what we have so far. We don't have X bar yet. We know that N is equal to 11 if you count up the number of data values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 data values. We are going to use a level of confidence of 95% with an alpha of 0.05. Alpha over 2 is 0.025. Sigma, it's definitely not available to us. And S, well, that has to be calculated as well. We'll use our spreadsheet to calculate our sample mean, or X bar, and the sample standard deviation. Let's go to a spreadsheet and do that. We'll put these numbers in. I have this spreadsheet right here. Here I just have some old data, but I'm going to have to type in the data manually. I'm going to get rid of the old data. And that's important to do. Make sure you get rid of all your old data on your spreadsheet. Now I'm just going to type the data in manually. 73, 84, 71, 84, 75, the mean, otherwise known as x bar. In order to calculate that mean, we just use the can spreadsheet function. We would say equals average, open parenthesis, grab the first one, go all the way down to the last one, and we would close parenthesis, press enter, and we have 75.454545 S. That's the sample standard deviation, and hopefully you remember from way back, equals STDEV dot S. And open parenthesis, we're going to grab the first one and go down to the last value, close our parenthesis, and press enter. And we already have as 11 values. Remember, there are 11 values here. I'm just going to copy these values on the left-hand column by doing a direct cell reference. Equals, x bar is the same as mean. N is equal to 11. New, that equals, we'll click on the cell with N and then subtract 1. My level of confidence is 0.95. Remember, none was stated in the problem. Alpha, that's going to equal 1 minus my level of confidence, stated as a decimal. Alpha over 2 equals alpha divided by 2. And mu is equal to 80. This S is taken directly from this here. That was a calculated value. I'll just type in equals and direct cell reference that. Remember, if we are testing means and sigma is not known, the correct sampling distribution happens to be the t distribution. So we will type in equals t dot inv, open parenthesis, alpha, comma, nu, otherwise known as degrees of freedom. My right tail critical value equals, if you remember correctly, it's the absolute value of the left tail, absolute value of the left tail critical value. For two tail with the t distribution, we do not use the alpha over 2 value, even though I have it shown right here. Instead, what I do is I use the alpha value, I just use a different function. I use the t.inv.2t function equals t dot inv dot 2t, and you see all the way down here, that's what it says. Open parenthesis, and we'll still use alpha, comma, nu, close parenthesis. Now I have my x bar and my sample standard deviation for this problem, and I have all the inputs that I need for this problem. We know that this is a test about a population mean and keywords mean or average. This is a test of mean, but sigma is not known. We use the t distribution. The keywords makes a difference, meaning either side, it just makes a difference. It's a two-tail test. Because we know that mu is equal to 80, that was given to us up here in the problem, we have mu equals 80 for the null hypothesis, and the alternate hypothesis is mu is not equal to 80. We need to determine the critical values. We've already done that on the spreadsheet. Because it's a two-tail test, remember, we use t.inv.2t. We ended up with a critical value of plus or minus 2.228. You could see on the spreadsheet, that's what we have right over here. This is what the image looks like. We have a critical value at negative 2.228, which is right about here where this red line is. And we have one at positive 2.228, which is right here. Where this red line is, we, in a sense, have two rejection regions. And if my test statistic falls in either rejection region, then we would reject the null hypothesis. And of course, if it doesn't fall in either one, then we would fail to reject the null hypothesis. In order to calculate the test statistic, we've already done this once or twice before. So we would use this formula because this is the one where we have an S or an approximation for S. We happen to have S with the small data size that we have. And let's type in the formula as shown right over here. We would type in, clicking on the cell where it says test statistic, equals, open parenthesis. Click on the cell with the mean, or X bar, minus the cell that contains mu, divided by, open parenthesis, the cell that contains S, over the function for square root is sqrt, open the square root parenthesis, and we click on the cell that has n, close the square root parenthesis, close the parenthesis for the denominator, and press enter. And you see we have negative 2.496, almost negative 2.5. We compare this number to our two-tailed critical value, but let's take a look at what this looks like on a diagram. You can see right here that because the critical value is plus or minus 2.28, and my test statistic falls in the rejection region that happens to be in the left tail, because negative 2.5-ish is way farther into the tail than 2.28 or negative 2.28. So what we do here is we reject the null hypothesis. But what does that mean? We reject the null hypothesis. What that means is that the foam obviously makes a difference, and good for us that it fell in the left side of this, which means that it actually did reduce the noise level. Since this is a two-tailed test, we have to be careful how we state the conclusion. We are rejecting the null, so we can say with a 95% level of confidence, it seems that the foam makes a difference in the decibel levels.